Here we go through two algorithms which tell you the shortest distance from one node to all other nodes, Dijkstra's and Bellman-Ford. They both work quite differently, and the situation you're given should determine which one will work best. We will start with Dijkstra, and the easiest thing is just to go through the process. So, first thing we do is initialize the source weight to 0, mark it permanent, and then set all of the other weights to infinity. Next, from the most recent permanent node, we relax all the edges to the adjacent nodes, which is to say we update them with a shorter path if possible. Now initially 0 is clearly the last node we made permanent, and the edges we can look at are these ones highlighted here. So 0 plus 3 is 3 for B, 5 for H, 3 for C, and 4 for D. Next, we select the unpermanent node with the smallest weight and mark it permanent. So in this case, I've chosen, there are a couple of options, but we've chosen C. We've marked it permanent, so it's got that darker blue. And now we just repeat this process. So now from C, the edges I can consider that go from C to non-permanent nodes are highlighted in red there. And you can see that it's quicker to go to H via C, because 3 plus 1 is 4, so we can update the label of H to 4. We can update E to 4 as well. 3 plus 1 is 4. We can update G to 5. And for D, it's also 4, so we don't need to update it. Now we choose the smallest unpermanent weight, which is B, which is 3. So we make that permanent. And the only edge we can consider now is BH. Now 3 plus 4 is 7. That's not better than 4, so nothing else to do there. Now we've got a couple of options for the next node to make unpermanent. Let's make it D. We make D permanent and we consider G and F. G doesn't get updated because 4 plus 5 is 9, which is greater than 5. We can update F to 11. And now we'll consider the smallest unpermanent node. We'll choose H, which lets us consider this edge to E, but doesn't make any difference because 4 plus 2 is 6, greater than 4. Now we are going to permanentize, however you say that, E, and consider edges from E. We've got 4 plus 4, which is 8, which updates F, and 4 plus 3, which is 7, which updates K. Now we permanent the 5, which is G, which is 5 rather, and we have to consider GF. 5 plus 5 is 10, that's no better than 8, so now we will permanent K, and then we'll consider from K to F, which is still bigger than its existing value, so we make F permanent and we stop the algorithm. Note that if we want just to get to one place in particular, we can stop when that node is made permanent. To be safe in algo exams, state whether you are finding the distances to all nodes from the source or just one particular node, depending on the context. Now, the next step is to work out the actual path, and let's say we wanted to get to F. I think that's the most interesting one. We reconstruct the path by starting at, in this case, F, or the destination, and we look at every edge, and we want it so that F minus the edge gives us the resulting label on that node. So for example, F to K, 8 minus 2 is 6, which is not 7, so we're not going to consider FK. F to E, 8 minus 4 is 4, so we can consider that. And the other two edges don't work either. So we have to consider, we're going to go, the last part of our path will be EF, so we lock that one in. And now from E, we do the same thing. We say, well, EH, 4 minus 2 is not 4, so that's no good. EC, 4 minus 1, 3. So let's choose that one, lock that one in. It's kind of obvious where this is going, but we'll consider all of them. 3, so C minus H, 3 minus 1 is not 4, but C minus A, 3 minus 3 is 0, so that gives us our final path. So reconstructing the path is now A, C, E, F. At this point, you should aim to practice doing another one of these yourself. Next, we look at Bellman-Ford. This works by iterating over all edges a number of times, rather than the most recent vertex. This time, we'll look at the pseudocode a bit more explicitly. Because of how fiddly it is to carry out the algorithm, I don't think you'd actually be asked to do it in an exam, but examiners do often ask about negative cycles and some of the features of the pseudocode. So first off, we initialize two arrays. We've set this weight of A to be 0, the rest of the weights to be infinity, and we don't actually have to have predecessor handling here. We could reconstruct the path in the same way we did for Dijkstra, but this version shows you how we can maintain the path using predecessors. Now we do this v-1 times, so in this case there are 9 vertices. We would do this 8 times. We actually won't do it 8 times, so if you're getting bored halfway through, don't worry, we're only going to do it about 3 times for reasons that I will explain. So we start with A. I've highlighted the edges we're going to be using, although in theory we should be looking at every edge. What we're saying is the edge A, B, if I go from A to B, so 0 plus 3 is 3, is that better than infinity? Well, yeah, clearly it is. If I consider, just for example, the edge from H to E, well, H is infinity at the moment, so H plus 2 is still infinity, which is infinity, so it doesn't help. So when we're doing this by hand, there's only certain edges we have to really look at. So we update B, C, D, and H. Now we go through again, and we update, we can look at edge CH, so C has a weight of 3, plus 1 is 4, so we can add that to H. CG is 2, so we can go 3 plus 2 is 5 for G. DF is 7, so we can do 4 plus 7 is 11 to find the weight for F. And CE, same thing, 3 plus 1 equals 4. Next, we can consider E to K, so that's going to be 4 plus 3, which is 7. We can consider E to F. Now, E had a weight of 4, plus 4 is 8, which is better than the 11, so we've changed that now. See, it was 11, now it's 8. Now, in theory, we would keep doing this. I've only been examining, like for the purpose of talking it through, I've only been examining particular edges, but the algorithm would examine every edge every time. So we can imagine it's quite time consuming. When we think about what happens at each pass, notice for the first iteration, we had all the shortest paths of length 1. Then for the second iteration, all the shortest paths of length 2. And we did I equals 3, we got to the third iteration, and I think we can see just by inspection that the shortest path has a length of 3 edges, so we don't need to go any further. You can see it's rather fiddly to do this, so we're more likely to get questions around the algorithm rather than saying, do the algorithm. And one of the key things with Bellman-Ford is the negative cycle detection. So to look at this, this is the second part of code which handles that negative cycle detection. To just show you this in practice, we're going to start with a small undirected graph with a negative cycle. And you can see, I mean, if we went A, B, C, the whole thing has a weight of -1. And the reason we will see no shortest path exists is that we could just spin around this cycle and get the weight of any path to be as low as we wanted. So Bellman-Ford detects the negative cycles, but if that happens, it means there is no shortest path. So first pass, we update B to 2, C to 1. Now it actually gets a bit hairy here. When we update the -4 edge, like which way do we consider it? And this is something I'll mention now rather than earlier. Bellman-Ford only really works on directed graphs. Now what we should do is turn each edge into 2 edges, but even that now becomes a bit nonsensical because we end up with a cycle just between B and C. We've got BC is -4, CB is -4, and straight away we get some nonsensical results. So I'm going to start again, change this graph to make it directed. And we can see on the first pass, we would make B equal to 2. On the second pass, we make c equal to -2. So there were 3 vertices, we've done 2 passes. Now we do the second bit of code, and we're just doing the same thing again, but only once. And we can see that A now has a shortest distance of -1. And because that's changed, if at any point after the v-1th pass, we can still update the graph, that means there must be a negative weight cycle. Now, why does that make sense? Well, we stop at the shortest paths of v-1, since any shortest path of v edges would have to visit a vertex more than once, which wouldn't usually make sense unless there was a negative cycle, which made it worth visiting a vertex more than once. Okay, in summary, here are the features of each of the algorithms. So Dijkstra by default is the shortest path from a single source to all other nodes, or you can stop when the target node is made permanent. Talk about it in those explicit terms in exams. Don't talk about Dijkstra versus modified Dijkstra, because there's been some ambiguity in the past. Dijkstra is fine for directed or undirected edges. We must have non-negative edges to guarantee correctness. Like sometimes Dijkstra will give you a correct answer with negative edges, but we can't be sure. And Dijkstra we didn't mention before, but it follows that greedy design pattern of choosing the best course of action at each stage. Dijkstra is generally faster, especially for sparse graphs. So that means graphs that have a low number of edges relative to the number of vertices. So not a complete graph, let's say. For exams, you may be asked to apply the algorithm and you may be asked to answer questions around it. We'll cover explicit time complexities in another video. For Bellman-Ford, same thing, shortest path from a single source to all other nodes. Bellman-Ford requires directed graphs, or we require the undirected edges to be turned into 2 different edges in each direction. It's fine with negative edges if they don't make a negative cycle. If there is a negative cycle, it will detect them. In exams, I think the questions are more likely going to be talking around the algorithm rather than actually carrying it out. As always, leave comments, questions if you have anything you'd like explained in a bit more detail.